Okay, this is the second half of lesson 7.1 on sampling distributions. So here is an example of a population distribution where 50% are red. I think we talked about that example last time. So these are two individual samples of that data. So kind of like I did on my calculator where I simulated picking out 20 at a time. Those are two different samples of size 20. We would probably do a bunch of size 20 samples there to make up a sampling distribution. In fact, that's what they've done. Here they've said that this is the sampling distribution of all the possible ones that are there. Okay. So the population distribution is the original 50% red, 50% blue. That's just the population distribution is called. I don't think you have to know this as much, but that's one of the samples we're taking from that of size 20. This is the other word you need to know. That's called the sampling distribution of the sample proportion there. So it's a sampling distribution basically. So these terms just get a little bit confusing here. So don't just say the distribution, because what are you talking about? The population distribution or the sampling distribution? Does it make sense? So you got to specify which one you're talking about. Try not to call it the sample distribution. It's either the population distribution or the sampling distribution. So you don't want to just lose credit on little stuff like that. So a statistic is used to estimate a parameter that is an unbiased estimator if the mean of the sampling distribution is equal to the value of the parameter being estimated. So if we took 20 chips, we'd get exactly 0.5. So that we took every possible sample of that size, we would get the exact value of the population, which is 50% there. If you remember the sampling heights, we did do the range thing. And so is range an unbiased estimator? Not so much here, because the range of the sampling distribution was 3.67. That's the average range. But the actual range of the population was actually 7. So those don't match. So with range, it's not a good predictor there. It's not an unbiased estimator. It'd be a biased estimator, I guess. To get a trustworthy estimate of an unknown population parameter, start by using a stat that's an unbiased estimator. These are the two we used most often. So, p hat is the sample proportion of folks, and that's going to estimate the actual proportion, the true proportion, so to speak. The larger the random samples tend to produce estimates that are closer to true population values. So we want, like of these two, so this one was size 100, this was n equals 1,000. So you're looking at much more. So this is going to be much more accurate, much more precision there, less variability, and more accurate in everything it's trying to predict. It's pretty obvious usually. So if you want to estimate p, use p hat. You want to estimate mu, use x bar. So those are the population and parameters and the sample statistics there. This gives kind of a look at big picture what we want. So that the target in the top left, if you have a high degree of bias, you're not going to hit the target very accurately. The top right, that doesn't have a lot of bias, but it has high variability. That means you might hit the target, but it's not. It's going to be kind of sporadic. If you have high bias and high variability, that's not a good combination. You're not even going to hit the target at all, probably. Very little. Estimator with no bias and very low variability would be very close to the target center. That's obviously what we want. We want less variability, and no bias. So start using words like, I feel like in first semester, I probably was probably generous and probably gave you points when you said it was more accurate. But actually, you want to talk about precision here. So it was not very precise, or it was more precise. than more accurate. It's better to use words like precise than accurate. You might think they mean the same thing, but in stats, it's not really the case. That's what it says there. Basically, try to use, it was really more precise. Like there's less variability, it's more precise, those kinds of things. Okay, that's the lesson. Basically, let's look at a few examples. List all 10 possible samples of size 3. Like we did before, I'm just going to see why there are 10. So if I went to menu probability combinations and I did 5, because there's 5 different things, choose 3, there are 10 possible options there. You could start thinking about those 10s, like 93 and 87 can be paired with 96. 93 and 87 can be paired with 78. 93 and 87 can be paired with 90. And pretty soon you can write them all down. Just try to be systematic when you do that and write them all down. Calculate the mean of each sample and display the sample distribution as a dot plot. So to find the mean of that first sample, this is actually finding the sampling distribution if you wanted to find it. If you were asked this, it would be a small enough number here. There's only 10 possibilities that it's kind of manageable. It's kind of a pain to do this, but it's manageable. So the first average would be 92, and you calculate the second average and so forth, and you get 86 when you do that, and 90 and so forth. And then you just plot those on a dot plot, and you can see kind of a picture. Not sure what the X bar is there of the average of the sampling distribution is, but guessing it's around 88. This is a guess. We could probably figure it out if we needed to. Calculate the range of each sample and display the sampling distribution using a dot plot. So range would be the largest minus the smallest. So 96 minus 93 is 6. And so you just calculate, 93 minus 87 is, 96 minus 87 is 9. That would be the correct, the largest minus the smallest there is 9. And so you just plot all those values, find the range of each of the group of 3, plot those values on there. You can see that the typical range is about 12 if we averaged all those. Okay, in the pick 3 example, we create a sample distribution as sample mean for size n equals 3 and so forth. Is a sample mean an unbiased estimator of the population mean? I think so. You could actually add those up. So you could add up, let me see. So 85 plus 86 plus 87 plus, there's another 87 plus 88 plus 89 . So divide by 1, 2, 3, 4, 5, 6. Should have done that, but 10. And if we added up the 5 different values there, the first one was 93. So 93 plus 87 plus 96 plus 78. So this is the population, divided by 5, population mean is 88.8. So the mean of the sampling distribution that came from the dot plot was 88.8. That's called X bar. The mean of the population, those 5 numbers there, would be the mu, which is called a parameter, population parameter there. It's also 88.8. So is it an unbiased estimator? Absolutely it is, right? The mean of sample distribution to the sample mean is equal to the variable it's trying to estimate. So it is an unbiased estimator. Okay, that was quick. That's your lesson for today.